So here we'll talk about the inverse of a matrix. So you cannot divide anything by a matrix. A matrix division doesn't make sense. But instead, we can multiply by the inverse. So this would be like saying you cannot divide by 2, but you can multiply by a half. So it is a multiplication, but it works the same basic way as division. So first, we need to define the identity matrix. And this is going to be a square matrix with 1s on the main diagonal and 0s everywhere else. So here's the 2 by 2, the 3 by 3, and the 4 by 4 identity matrix. And this acts like 1. Basically, any matrix times the identity is equal to itself. So it's just like the 1 matrix. So an inverse of a square matrix, A, is any matrix C such that AC is equal to the identity and CA is equal to the identity. If it has an inverse, we say it's invertible. And this is actually unique. We're going to denote it by this A to the -1, which is just read A inverse. So I'm actually going to prove this is unique. So my proof. Anytime you want to show something's unique, let's start with 2. So we're going to let B and C be inverses of A. So, by definition of an inverse, AB is equal to the identity, and AC is equal to the identity. So this is just definition of what it means to be an inverse. Since they're both equal to the identity, they're equal to each other. And now I'm going to multiply on the left-hand side of both sides by B. If you multiply on the left of one side of the equation, you have to multiply by on the left on the other side of the equation. I can switch parentheses as much as I want as long as I keep everything in the same order. So BA times B is equal to BA times C. But by definition of an inverse, B times A is just the identity. So I have that IB is equal to IC. And multiplication by the identity doesn't change anything. So we actually have that B is equal to C. So having 2 inverses means, well, they're equal. So in reality, there's really only 1. Let's determine if these are inverses. Well, in order to determine that, we need to multiply them. We need to see first if A times C is equal to the identity. So let's multiply these. First row times first column gives me -21 plus 22, which is 1. First row, second column, gives me 6 minus 6, which is 0. Second row, first column, gives me -77 plus 77, 0. And then second row, second column, gives me 22 minus 21, which is 1. So that's what we wanted. But we also need to check the other way as well. Since matrix multiplication is not commutative, we cannot just switch the order of matrix multiplication. So we do need to check both directions. So -7 times 3 plus 2 times 11, that's 1. Here we have -14 plus 14, 0. 33 minus 33 is 0. And then 22 minus 21. So are these inverses? Yes, they are. So how do we find the inverse? We're going to start with a 2 by 2 matrix, and then we'll talk about the bigger cases. So if A is a matrix, A, B, C, D, then if AD minus BC is not equal to 0, we find the inverse by 1 over ADB minus BC times D minus B negative CA. So this is found by switching the elements on the main diagonal and changing the sign on the other two. And if AD minus BC is equal to 0, the matrix is not invertible. So let's do this one. AD minus BC is equal to, well, 6 times 3 is 18, minus 9 times 2, also 18, which is 0. So this particular matrix is not invertible. Now let's look at this one. 7 times 2 is going to be 14, minus 3 times 5, which is 15. So this time we get negative 1, so it is invertible. And we find this by doing 1 divided by this AD minus BC times, we switch the elements on the main diagonal, and we change the sign on the other two. Multiplying through by the negative 1 out front gives negative 2, 3, 5, minus 7.